A telescope just locked onto something impossible. An object moving through our solar system at 87 kilometers per second, far too fast to be gravitationally bound to the sun. On October 19, 2024, the Japan Subaru telescope confirmed what astronomers had suspected for weeks. This is 3I Atlas, the third confirmed interstellar visitor to enter our cosmic neighborhood. And according to data published in the Astrophysical Journal, its behavior doesn't match anything we've seen before. Light takes time to travel. When you look at the moon, you see it as it was 1.3 seconds ago. Look at our sun, and you witness light that left 8 minutes before. Gaze at the nearest star beyond our sun, Alpha Centauri, and you see light that began its journey over 4 years ago. This is confirmed science. Every photon crossing space carries an image of when it began its journey. And right now, photons reflecting off 3I Atlas are telling us a story that challenges everything we thought we knew about interstellar objects. Before we dive deeper into what makes this discovery so extraordinary, hit that subscribe button and turn on notifications. This is Cosmic Outliers, where we investigate the objects that break our models. Drop a comment with your theory about what we're really seeing here, because the data we're about to examine raises more questions than answers. The detection happened almost by accident. Astronomers at the Pan-STARRS Observatory in Hawaii were conducting their routine survey of near-Earth objects when they spotted an unusual light signature. The object appeared as a faint streak moving against the background stars. Its apparent magnitude measured around 18, far too dim for human eyes but clearly visible to modern telescopes. The team immediately recognized something strange. The trajectory was wrong. Most objects in our solar system follow elliptical paths around the sun. Their orbits are predictable, governed by Kepler's laws and Newton's gravity. But this object showed a hyperbolic trajectory, meaning it was moving too fast to be captured by the sun's gravity. It was passing through, not orbiting. Within 48 hours, observatories across 3 continents confirmed the detection. The European Southern Observatory in Chile, the Keck Observatory in Hawaii, and the Hubble Space Telescope all turned their instruments toward this intruder. Spectroscopic analysis began immediately. When scientists split the object's reflected light into its component wavelengths, they expected to see the familiar signature of ice and rock, the standard composition of comets. What they found instead was deeply puzzling. The spectrum showed absorption lines indicating the presence of water ice, carbon dioxide, and dust. These are normal comet ingredients, but the ratios were wrong. The abundance of certain molecules didn't match any comet in our solar system's catalog. More troubling was what they didn't see. There was almost no cyanogen, a compound typically abundant in cometary nuclei. The absence suggested either an unusual formation environment or a composition that defied standard models of how icy bodies form. Trajectory calculations revealed the object's hyperbolic excess velocity, the speed it would retain even at infinite distance from the sun. The number came out to approximately 35 kilometers per second. This confirmed beyond doubt that 3I Atlas originated outside our solar system. Its path traced back through interstellar space, and forward projections showed it would eventually leave our solar system entirely, traveling on into the darkness between stars. Here's where the data becomes genuinely strange. As observatories continued tracking 3I Atlas over subsequent weeks, they noticed something unexpected. The object was accelerating, not in the way gravity would predict, but showing a non-gravitational acceleration component. This means something besides the sun's gravity was affecting its motion. For normal comets, this phenomenon is well understood. As they approach the sun, surface ices heat up and sublimate, turning directly from solid to gas. This outgassing creates jets of material that act like tiny rocket engines, pushing the comet slightly off its gravitational trajectory. The effect is measurable and predictable, but 3I Atlas was different. The magnitude of acceleration didn't match the observed brightness or the estimated rate of outgassing based on spectroscopic data. The object appeared too faint to be producing the level of outgassing needed to explain its trajectory deviation. Teams at MIT and Harvard ran the calculations multiple times, checking for errors. The numbers remained inconsistent. Either 3I Atlas was outgassing material in a way we don't understand, or something else was influencing its path. One research team, led by Dr. Sarah Chen at Caltech, proposed an alternative explanation. Perhaps the object's surface properties were unusual. If 3I Atlas had an extremely dark, low-albedo surface that absorbed rather than reflected most sunlight, It could be outgassing more vigorously than its apparent brightness suggested. The dark surface would heat up more efficiently, driving faster sublimation of subsurface ices. This hypothesis required the object to have surface properties unlike any known solar system comet, but it remained within the bounds of natural phenomena. Another possibility involved the object's rotation. Detailed photometric observations, measurements of how the object's brightness changed over time, revealed a light curve with a period of approximately 7.3 hours. This suggested 3I Atlas was rotating, tumbling end over end as it moved through space. If the object had an irregular shape, and if outgassing was concentrated on one side or in specific active regions, the jets could create a complex pattern of thrust that didn't align neatly with simplified models. This explanation was plausible, but required a very specific geometry and distribution of volatile materials. What troubled researchers most was the comparison to previous interstellar visitors. In 2017, astronomers discovered Oumuamua, the first confirmed interstellar object. Oumuamua showed similar non-gravitational acceleration, but its case was even more perplexing because no outgassing was detected at all. No comet-like coma, no tail, no spectroscopic evidence of sublimating ices, yet it accelerated anyway. The discovery sparked intense scientific debate and even speculative proposals about artificial origins, though most scientists favored natural explanations involving exotic ices or unusual surface properties. Then came 2I Borisov in 2019, the second interstellar visitor. Borisov behaved like a normal comet. It showed clear outgassing, a visible coma and tail, and its non-gravitational acceleration matched predictions based on observed activity. Borisov fit the models perfectly. It was comforting in a way. The universe still made sense. Now 3I Atlas arrives, and it falls somewhere between Oumuamua's extreme anomaly and Borisov's reassuring normalcy. It shows some outgassing evidence, enough to be visible in spectra, but not enough to fully explain its acceleration. This intermediate state is arguably more frustrating than either extreme. With Oumuamua, scientists could propose exotic mechanisms because there was no outgassing to constrain theories. With Borisov, everything worked as expected. But 3I Atlas gives us just enough familiar behavior to rule out the most exotic explanations, while still refusing to fit conventional models. The object's estimated size compounds the mystery. Based on its brightness and assumptions about surface reflectivity, astronomers calculated 3I Atlas measures between 500 meters and 2 kilometers in diameter. That's substantial, comparable to many near-Earth asteroids. An object this large should behave predictably. We have centuries of data on how kilometer-sized icy bodies behave when they approach the sun. They follow known patterns. They don't surprise us, except this one does. Researchers attempted to determine the object's precise origin. Where in the galaxy did 3I Atlas begin its journey? Tracing the trajectory backward through space is complicated by the sun's motion around the galactic center and the gravitational influence of nearby stars. Computer simulations ran millions of possible paths, accounting for uncertainties in measured velocity and position. The results pointed to a region of sky in the direction of the constellation Perseus, but that's an area spanning hundreds of light years and containing thousands of star systems. Pinpointing a specific stellar birthplace proved impossible with current data. One intriguing possibility emerged from the trajectory analysis. The path suggested 3I Atlas might have encountered a close pass by a star approximately 300,000 years ago. Such an encounter could have perturbed its orbit, sending it on a trajectory toward our solar system. If true, this meant the object had been traveling through interstellar space for hundreds of thousands of years before we detected it. During that time, cosmic rays would have bombarded its surface, potentially altering its composition and creating exotic chemistry impossible to replicate in laboratory conditions on Earth. The cosmic ray hypothesis offered a potential explanation for the unusual spectroscopic signatures. High-energy particles striking the surface over millennia could break down organic molecules, create new compounds, and alter the distribution of volatiles just beneath the surface. When 3I Atlas finally approached the sun and began heating up, these radiation-processed materials might outgas in unexpected ways, producing the anomalous acceleration we observed. Dr. Chen's team published a paper in Nature Astronomy proposing this radiation processing model. They calculated the expected dose of cosmic ray exposure over 300,000 years of interstellar travel and modeled how this would affect various ice compositions. Their simulations suggested that certain exotic ices, particularly carbon monoxide ice and highly volatile organics, could be preserved beneath an insulating crust of radiation-darkened material. When solar heating penetrated this crust, the exotic ices would sublimate violently, creating outgassing strong enough to accelerate the object, while remaining partially hidden from direct spectroscopic observation. The paper was well received but not universally accepted. Other research groups pointed out that the model required a very specific layering of materials and a precise balance of surface properties. If the crust was too thick, no outgassing would occur. Too thin, and the volatiles would have been lost long ago to slow sublimation during interstellar travel. The window of viable parameters was narrow. Possible, yes, but requiring a degree of fine-tuning that made some scientists uncomfortable. An alternative explanation came from a team at the University of Tokyo. They proposed that 3I Atlas might be a fragment of a larger body that broke apart during its interstellar journey. If the object was once part of a planet or large moon that suffered a catastrophic collision, the fragment might have an exposed interior with unusual composition. Planetary interiors contain materials formed under high pressure and temperature, substances that rarely appear on cometary surfaces. If 3I Atlas was such a fragment, it could contain high-pressure ices or minerals that sublimate at temperatures and rates different from normal cometary materials. This fragmentation hypothesis had appeal because it explained both the compositional anomalies and the unusual outgassing behavior. It also addressed a puzzle that had bothered researchers: the object's apparent strength. Photometric data suggested 3I Atlas maintained a relatively stable rotation state, despite the torques created by asymmetric outgassing. Normal cometary nuclei are fragile, loosely bound collections of ice and dust that can fracture or disintegrate under stress. The stability of 3I Atlas hinted at a more coherent internal structure, consistent with a fragment of a larger differentiated body. Testing these hypotheses required more data. The James Webb Space Telescope turned its powerful infrared instruments toward 3I Atlas in early November 2024. Webb's sensitivity in the infrared spectrum allowed it to detect thermal emission from the object's surface and probe the composition of outgassing materials with unprecedented detail. The observations took place over 3 nights, capturing the object at different rotational phases to build up a complete picture of surface variations. When the Webb data arrived, it revealed something no one anticipated. The object's thermal emission showed temperature variations across its surface that couldn't be explained by simple solar heating alone. Certain regions appeared significantly warmer than others, even accounting for rotational effects and viewing geometry. The hotspots didn't correlate with areas of expected outgassing activity. They appeared in locations that should have been relatively inactive based on models of comet behavior. One particularly anomalous hotspot measured temperatures approximately 40 Kelvin higher than surrounding areas. For reference, that's a substantial difference in the cold environment of the outer solar system, where 3I Atlas was located during observation. The excess heat required an internal energy source or an exotic surface process. Neither option fit comfortably within conventional comet physics. Dr. Michael Torres, lead investigator for the Webb observations, stated in a press conference that the temperature anomalies suggested possible subsurface pockets of heat retention or chemical reactions occurring beneath the surface. He was careful to emphasize that all proposed explanations remained speculative and required further investigation, but the message was clear. We were looking at something that didn't behave like a typical icy body. The Webb data also provided the most detailed compositional analysis yet. Spectroscopic observations in the mid-infrared detected the signatures of water ice, carbon dioxide, methane, and several organic compounds. But buried in the spectrum were faint absorption features that didn't match any known reference materials. These mystery lines appeared at wavelengths corresponding to complex organic molecules or possibly minerals formed under high-pressure conditions. The team spent weeks trying to identify these features, comparing them to laboratory spectra of hundreds of candidate compounds. None matched perfectly. This is where scientific methodology requires careful distinction between observation and interpretation. The observations are clear. Webb detected specific absorption features in the infrared spectrum of 3I Atlas. That's confirmed data. What those features represent, however, remains uncertain. They could be exotic ices we've never encountered in solar system objects. They could be complex organic tars created by radiation processing. They could be high-pressure minerals from a planetary interior. Or they could be something we haven't considered yet. The honest answer is, we don't know. What we do know is that 3I Atlas doesn't fit our existing models of interstellar objects. We have a sample size of 3 confirmed interstellar visitors. Oumuamua was bizarre and unlike anything in our solar system. Borisov was perfectly normal, a textbook comet from another star. And now 3I Atlas occupies a strange middle ground, showing enough familiar characteristics to be recognizable as a comet, while displaying enough anomalies to defy complete understanding. This pattern raises an important question about selection bias and detection limitations. We can only discover interstellar objects that pass close enough to Earth and are bright enough for our telescopes to detect. The 3 objects we found might not be representative of the true population of interstellar wanderers. Perhaps the galaxy is full of Borisov-like normal comets and Oumuamua and 3I Atlas are rare exceptions. Or perhaps most interstellar objects are strange and Borisov was the outlier. We can't know with a sample size of 3. Current estimates suggest that at any given time, there might be thousands of interstellar objects passing through the inner solar system. Most remain undetected because they're too small or too dark, or their trajectories don't bring them close enough to Earth-based telescopes. The upcoming Vera Rubin Observatory, scheduled to begin operations soon, will dramatically increase our ability to detect faint, fast-moving objects. When it comes online, we expect to discover dozens or even hundreds of interstellar visitors per year. That flood of data will finally give us the statistical sample needed to understand what's normal and what's exceptional among these cosmic travelers. Until then, we're left analyzing the few examples we have, and 3I Atlas continues to confound us. As it moves farther from the sun, outgassing activity should decrease as temperatures drop. Observations in late November confirmed this prediction. The object's brightness faded, and spectroscopic signatures of active sublimation weakened. But the non-gravitational acceleration persisted longer than models predicted. The object kept accelerating, even as direct evidence of outgassing disappeared below detection thresholds. This extended acceleration period forced researchers to consider whether the anomalous behavior might be caused by something other than conventional outgassing. Perhaps the object had structural asymmetries that created pressure imbalances as its interior temperature slowly equilibrated with space. Perhaps there were deep subsurface voids containing trapped volatile gases that leaked out through cracks over extended periods. Or perhaps the acceleration was caused by radiation pressure effects we hadn't properly accounted for in our models. Each explanation had problems. Structural asymmetries should produce predictable, consistent acceleration that correlates with the object's rotation. The observed acceleration showed variations that didn't match the rotational period. Subsurface voids required a very specific internal structure and precise crack networks, which seemed unlikely for a tumbling object that had survived interstellar travel. Radiation pressure effects should be minimal for an object this size and at this distance from the sun. A research team at the European Space Agency proposed using future space missions to investigate interstellar objects directly. Instead of observing from Earth, they suggested sending a fast probe that could intercept an interstellar visitor and conduct close-up measurements. The technical challenges are immense. Interstellar objects move at high velocities, and matching their trajectory requires enormous amounts of fuel. But the scientific payoff would be transformative. Direct sampling of the surface, measurements of magnetic fields, detailed mapping of temperature variations. All of this would provide data impossible to obtain from Earth-based observations. The proposal generated significant interest but faced the reality of budget constraints and long development timelines. Designing, building, and launching such a mission would take at least a decade. By then, 3I Atlas would be long gone, far beyond the reach of any spacecraft we could build. The mission would need to target the next suitable interstellar visitor, whenever that might appear. And we'd need to detect it early enough to plan and execute an intercept trajectory, which requires the object to be discovered while it's still approaching the inner solar system, not after it's already leaving. Meanwhile, ground-based observations continued squeezing every possible piece of information from 3I Atlas before it faded from view. Radio telescopes searched for any signs of emissions that might indicate unusual electrical activity or interaction with the solar wind. Nothing was detected. X-ray observatories looked for evidence of particle impacts or magnetic field interactions. Again, nothing unusual appeared. The object seemed inert in every wavelength except the optical and infrared bands where its reflected sunlight and thermal emission could be measured. By December 2024, 3I Atlas had moved beyond the orbit of Mars, heading outward toward the asteroid belt and eventually the outer solar system. Its apparent brightness had dropped to magnitude 22, requiring the largest telescopes to detect it. Within a few months, it would fade beyond the detection limits of even our most powerful instruments. The object would continue its journey into interstellar space, eventually passing beyond the heliopause and leaving the Sun's domain entirely. In a few 100,000 years, it might encounter another star system, carrying with it the subtle perturbations from its brief passage through ours. The scientific community published dozens of papers analyzing various aspects of 3I Atlas. Teams examined its rotation state, surface composition, thermal properties, trajectory evolution, and potential origin. Each paper added pieces to the puzzle, but the complete picture remained frustratingly unclear. What we learned can be summarized in what we confirmed versus what we're still debating. Confirmed observations. 3I Atlas is an interstellar object with a hyperbolic trajectory. It measures between 500 meters and 2 kilometers in diameter. It shows spectroscopic evidence of water ice, carbon dioxide, and organic compounds. It exhibits non-gravitational acceleration inconsistent with observed outgassing rates. It has an irregular rotation with a period near 7.3 hours. Its spectrum contains unidentified absorption features. Thermal observations reveal anomalous hotspots, leading theories under debate. The object might be coated with radiation-processed materials from extended interstellar exposure. It could be a fragment of a larger differentiated body. Subsurface volatile reservoirs might be driving hidden outgassing. Exotic ices or high-pressure minerals might be present. The non-gravitational acceleration might result from complex torques and internal structure we don't fully understand. What remains genuinely uncertain: the exact composition of mystery spectral features, the nature of the thermal anomalies, the true cause of the persistent acceleration, the object's precise origin and history, whether 3I Atlas represents a common type of interstellar object or a rare exception. This uncertainty isn't a failure of science. It's how science works when confronting genuinely new phenomena. We observe, we measure, we propose explanations. We test those explanations against new data. Sometimes the data confirms our models. Sometimes it forces us to revise them. And sometimes, as with 3I Atlas, it reveals that our models are incomplete. The broader implications extend beyond this single object. If interstellar space contains a diverse population of bodies with compositions and properties unlike anything in our solar system, it means planetary formation and evolution can produce outcomes we haven't witnessed in our own cosmic neighborhood. Every star system might create unique types of objects shaped by specific formation conditions, stellar compositions, and evolutionary histories. The galaxy could be filled with exotic materials and structures that challenge our Earth-based intuitions about how matter behaves. This possibility is both humbling and exciting. Humbling because it reminds us how limited our perspective is. We've studied one star system in detail, ours. We've analyzed samples from a handful of bodies: the Moon, Mars through meteorites, a few asteroids and comets via return missions. That's our ground truth for understanding planetary science. When interstellar objects arrive carrying materials from other systems, they expose the gaps in our knowledge. But it's also exciting because each new discovery expands our understanding of what's possible. Before Oumuamua, we didn't know interstellar objects passed through our solar system at all, or we assumed they were so rare we'd never detect one. Now we know they're relatively common. Before 3I Atlas, we might have assumed all interstellar comets would behave like Borisov. Now we know that's not true. The universe keeps teaching us that it's more diverse, more complex, and more interesting than our theories predict. Looking forward, the key to understanding interstellar objects lies in increasing our sample size. 3 examples aren't enough to draw firm conclusions about populations and categories. We need dozens or hundreds. The Vera Rubin Observatory will help dramatically. Its wide-field camera will survey the entire visible sky every few nights, detecting faint, fast-moving objects that current surveys miss. When it begins operations, the rate of interstellar object discovery should increase by orders of magnitude. Additionally, advances in spectroscopic instruments and adaptive optics systems will allow more detailed characterization of detected objects. We'll be able to measure compositions with greater precision, resolve surface features, detect fainter outgassing signatures, and track subtle variations in brightness and color. Each improvement in observational capability reveals new details that constrain theoretical models. There's also hope that some interstellar visitors might be more accessible for direct investigation than others. If we detect an object while it's still far from the sun, moving relatively slowly on an incoming trajectory, there might be time to plan and launch a fast intercept mission using existing technology. Such a mission would be expensive and technically challenging, but not impossible. The scientific return from direct measurements, actual samples of material from another star system, would be extraordinary. What 3i Atlas has taught us is that we can't make assumptions about interstellar objects based on limited data. Each visitor brings its own story, shaped by a formation environment and evolutionary history we can only infer from fragmentary evidence. Some will fit our models, others will break them, and that breaking of models is where the most interesting science happens. As 3i Atlas fades into the darkness beyond Mars, moving on its lonely journey back into interstellar space, it leaves behind more questions than answers. That's not a failure. That's an invitation to build better instruments, develop more sophisticated models, and remain humble about the limits of our knowledge. The universe is vast, ancient, and full of phenomena we're only beginning to understand. Every interstellar visitor is a messenger from that larger cosmos, carrying information about conditions and processes happening in stellar systems we can't yet reach. We finally captured 3i Atlas. We observed it, measured it, analyzed it with every tool at our disposal, and what we found breaks every simple model we tried to apply. But that's not the end of the story. It's the beginning of a new chapter in understanding how diverse the galaxy really is. The object that breaks our models is the one that forces us to build better ones. And in that process of breaking and rebuilding, we get closer to the truth about the universe we inhabit. If this investigation into cosmic anomalies expanded your perspective on what's possible out there, hit that like button. Subscribe to Cosmic Outliers if you want to follow along as we track down the universe's most perplexing mysteries. And drop a comment with your theory about what's really going on with 3i Atlas, because the best science often comes from questioning what we think we know. This is Cosmic Outliers, where we're mapping the impossible, one outlier at a time.